This is the screencast for section 4.4, example 4, 444. Designing a can. We've also designed cans in pre-calculus and found some, I don't know, minimum surface area maybe, or maximum surface area, sometimes volume. In this case, you have been asked to design a 1 liter oil can shaped like a right circular cylinder. See the figure. What dimensions will use the least material? So we're talking about surface area. And then as far as surface area is concerned, you don't measure surface area in any version of liters. So I'm going to change this 1 liter to 1,000 cubic centimeters and work with that instead. So I want the surface area of this can, which is going to be the top and bottom, so 2 pi r squareds, plus the circumference times the height to get the rectangular basically wrap around the can. I don't mind working with one of these variables, maybe radius, but I need another one. I need height, so that because I don't know surface area, I don't know radius, and I don't know height. So again, the other piece of information I'm given is this volume, and I know that the volume of a can is pi r squared times height, and I know that this volume is 1,000 centimeters cubed, so I can solve for height in terms of r and be able to substitute that back in. So now I have a new expression for surface area that doesn't involve height at all, it only involves radius. But I'm going to simplify a little bit, and we don't usually use 2 variables to describe any output. We use 1, so I will change that to area. But then now I did simplify, but the 2,000 over r, I'd rather not use quotient rule when I'm taking the derivative. I'd rather use power rule, so I changed that to 2,000 r to the -1. So now I'm going to take the derivative and then use my calculator here to find the 0 of a prime, which I get at 5.419. So to answer the question, what dimensions will use the least material? Well, the radius is going to be 5.419 centimeters, and then to find the height, I can just use this relationship, plug in the radius, so 1,000 over pi times the 5.419, or really this exact x value here, squared, and that'll get me the height of 10.84 centimeters. The now try problem, we're going to design a tank. Your Ironworks has contracted to design and build a 500 cubic feet square-based, open-top, rectangular steel holding tank for a paper company. Alright, so I got to draw that first so I know what that looks like and what that even means. Well, it's got a square base, which means its top is also going to be square, and then it's a rectangular holding tank, so it's like the sides are rectangular. The tank is to be made by welding thin stainless steel plates together along their edges. As a production engineer, your job is to find dimensions for the base and height that will make the tank weigh as little as possible. So weigh as little as possible. That sounds like volume, but not actually, because the volume of the tank is going to be filled with something else. We want to make the surface area of the tank at a minimum so that we're using the least amount of material. So that's surface area. So the surface area of this tank is going to be 1 bottom, not the top, so x squared, and then 4 of the sides, so that's 4 of the x's by h. Well, I can't work with all 3 of these variables, surface area, the x dimension, and the height. So I need to find another way to express height, hopefully in terms of x, and I have a volume of 500 cubic feet. So the volume would be 500 equals length times width times height, so x squared times h, meaning h is going to be 500 over x squared, so I can substitute that in. And with a little substitution and writing the x in the denominator as x to the -1, I can easily take the derivative then and find s prime, so I can find its minimum and make this tank weigh as little as possible. So I've got the first derivative, and I find, let's see, that it's got a 0 here at 10. I guess you could have just seen that and looked at it or solved by setting s prime equal to 0, or you could use your calculator. And I'm going to test that on a number line. And s prime changes from negative to positive at 10, so S therefore changes from decreasing to increasing, so there is a minimum of S at x equals 10. So if I make the tank 10 by 10 by, hold on a second, 500 divided by 10 squared, the height would be then 5. That would minimize the weight of the tank. Now part B asks us to briefly describe how you took weight into account. So in other words, how did you decide that weight equaled surface area? Now your wording for this can happen in various ways. Each of us is going to write this differently. So my goal is to explain how the weight of the tank is affected by how much the material is used, and then how that material used is really affected by the surface area, therefore getting us from weight to surface area, and then therefore minimizing weight minimizes surface area. So this is how I did that. I said the weight of the tank dry, because again we're not including the volume inside, is affected by how much material is used. So here I'm relating the weight to the material. The less material is used, the less the tank will weigh. So there's material to weight again. In order to minimize the amount of material used, the surface area of the tank needs to be minimized. So again, I'm connecting weight to surface area through the amount of material.